I could have started the quiz now, okay, and then started my lecture. But the thing is, people don't come on time. Okay, then I can't give different times for others. So let me start at 8:10. I will discuss for 10 minutes. Start at 8:10, finish it, and then again do 10 more steps. Because we are looking at limit theorems. Okay, the one thing is the weak law of large numbers. We will recollect what it is. Then we will at least illustrate the Stark law of large numbers. So we have IID random variables, and this need not only be IID. They need not be identical. They have to be independent. We can also generalize for non-identical distributions. So n random variables, IID random variables, x1 to xn, are a single experiment which you make n trials out of it. And each trial you get one, it's a random variable, the outcome is a random variable. So the realizations are x1 to xn, small x1 to xn, and you define the sample mean. What you do is, you add up all the realizations and divide it by m, and that is what is called as the sample mean. We are interested in the definition of sample mean and its utility. So mn is defined as x1 plus x2 to xn by n. So mn is the random variable, because it is a function of many random variables. So from here, this one it is a f of m1 by x1 to xn. So if you look at this random variable, its expectation will turn out to be the expectation E of x. This is the common expectation of this random variable. And common variance of x is sigma square. So E of mn will be follows that it will be its mean will be the same as the mean of the individual random variable. If you look at the variance of mn, so it is the variance of this one, sum of the variances. But if you have variance of a times x, it is a square into variance of x. So accordingly, you will get that this n, the denominator will become n square, because 1 over m square is 1 over m square, and it is the sum of n variances, n times variance of x, n times sigma square, n times variance of x by n square. So variance of x by n, variance of x is sigma square by n. So which we see that the mean is retained while the variance keeps on decreasing as n increases. So it will become more and more weak, and it will be more like a direct delta function. To make a concrete argument as to how it will convert to a deterministic value, we will apply the Chebyshev inequality, which states the probability that mn minus mu is greater than epsilon. That is, the sample mean deviates from the expectation, okay, by a value epsilon is given by this bound. It will be less than or equal to sigma squared by n epsilon squared. Okay. Why? Because it is less than or equal to variance of mn divided by epsilon squared. That is what Chebyshev inequality is. Variance of n is sigma squared by n epsilon squared. So as n increases, this becomes very, very small. So you will see that the probability that mn deviates from mu will be very, very small. What it means is that suppose you have got a biased coil, you want to know what is the probability of getting a head which you don't know. Then to get the estimate for the probability of success of a Bernoulli random variable, you conduct a lot of Bernoulli random trials, take the sample average, and that will converge. Okay, that will be the very good estimate for the expectation. That will give you the probability. So this is what it does. So that is the weak law of large numbers. Then we have got the strong law of large numbers. So that it will stay like that. So what here it tells is it's also the same thing we are looking upon. We have IID random variables xn whose realizations of xn to xn, and it will take the sample mean by n. What this tells is probability that m1 equal to mu. Approaches 1 x is 1. So if you look at this probability of this event occurring, this approach becomes very, very large. Of course, it's a probability. It can only become a maximum of 1, and approaches 1 in the limit intensity. These are all actually different ways of what we will discuss later, touch upon later in the conversion. It's called a stochastic conversion. How a sequence of random variables behave in asymptotic limits. There are different ways of convergence we will talk about. Convergence in probability, mean square convergence, almost sure convergence, and so on. But to an extent we can understand it. If you want to go deeper into it, it's a little mathematically intricate, but so in that sense, both are telling me nearly the same thing, but this is the way it's interpreted is as follows. Suppose you have tossing of a, let us say, a Bernoulli time. For example, you will take even the case of tossing of a coin resulting in a head or tail. When a head occurs, let us say you map it to random variable 1. Okay. So this is what you do. So, and let us say it is a fair coin, or let us say P is the probability of taking a head. So the probability P, when a head occurs, the random variable takes a value 0 or 1, and for the tail, it takes a value 0. This is what it happens. So, if you do one toss, then and then you look up the random variable, the event, that probability that a head will occur will be P. Now you do one more toss, then you look at the, and then if you take a sample mean, that is the number of times you toss, and then you head occurs, and then find the sample mean. That is you. So you may get 1 plus 0 or 0 plus 1 or 0 plus 0 or 1 plus 1, and then take average of. This is how it is. If you bear a fair coin, then what will happen is, this is what will happen. Accordingly, you will get some value. So the way it can happen is, so the following things can happen. Head, tail, head, and then head, and so on. For this one, the sample mean, okay, should be equal to, that is, you look at the various this one, and then you may get a head. Accordingly, you can assign a probability. So, there are certain events which will lead to the sample mean of half. Okay. So what events will lead to the, what cases will lead to the sample mean of half? These are the two cases, HT and HT. Right? Because HT means 1 plus 0. TH means 0 plus 1. So both of them, the total is 1. And the average is 1 by 2. So these are the two events which will lead to the case that m1 is equal to mu. Okay? So this is what happens. So this is the event which whose probability you can compute. But if you do more, then you will have three things, H, 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 all the way to T, 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 and so on. So if you have a large number of experiments being conducted, in the sample space, you will have an event. This is the event, okay, which is, let us consider this event, which is the set of all sequence of HTs whose average equal to mu. That is, you should have HT, H, 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 and so on, such that if you do an average, okay, some times H will accept divided by the total length, that will be equal to P. There are many such combination of H and T sequences, okay. If you take the corresponding sample mean, which will be wherever you have this one, you put 1 and then find this one, the number of times is equal to this one, the fraction that becomes P. Okay. Those are all will be in the event, because this is the event which corresponds to M1 is equal to P. So what this simply tells is, if the limit n tends to infinity, the probability will be concentrated in this one, which is those sequences whose sample mean will be equal to mu. These E complement, the probability will become lesser and lesser and will tend to 0, whereas all probabilities will get concentrated. That is what the strong law of large number essentially. Yeah, I will stop at this point.